So we're going to show the relationship between beta and gamma functions here. I have done at least 2 other videos where I have shown this relationship to hold, but the difference is in the transformation and how we approach establishing the relationship between the beta and the gamma function. So this is yet another way of doing this. We're going to start by replacing u in the gamma function that I have up here. We're going to replace u with x squared. And of course, when we differentiate, du becomes 2x dx. The limits of integration on u are from 0 to infinity, and once you plug in 0 for x, you square it, you get 0. And of course, as u goes to infinity, so does x squared. So the limits of random variable x are not going to change. They're going to remain from 0 to infinity. Next, I'm going to put the gamma of alpha. I'm going to write it using our new transformation, integral from 0 to infinity of x to 2 alpha minus 2 e to negative x squared times 2x dx. Okay, and then likewise we can do gamma of beta in just a moment, but let's simplify this one for now. I'm going to bring the 2 out in front. This is the integral from 0 to infinity of x to 2 alpha minus 1 times e to negative x squared. 2 alpha minus 1 times e to negative x squared dx. The reason it's minus 1 is because I multiply x times this x, and that's how the exponent is increased by 1. Alright, now the same thing holds for gamma of beta. So gamma of beta similarly can be shown to be 0 to infinity. This time we're going to use a different variable, y, to 2 beta minus 1 e to negative. This would be y squared. And of course dy, and there's 2 in front. Okay, now let's multiply gamma of alpha times gamma of beta. So gamma alpha times gamma beta is going to be what? It's going to be 4 times the double integral from 0 to infinity of x to 2 alpha minus 1, y to 2 beta minus 1, and then the e to negative x squared and e to negative y squared. You multiply them, you actually add the exponents with a common base e. And I have dy dx. Okay, now let's actually make a transformation at this point to evaluate this double integral. Our transformation xy is going to take us from xy coordinate system to a polar coordinate system comprised of r and theta. So we're making a polar transformation. And if you recall, in polar coordinate, x is given by r cos theta, and y is r sine theta. And so that when you do x squared plus y squared, you get r squared cosine squared theta plus sine squared theta, that's the Pythagorean identity. That gives you 1. So x squared plus y squared is simply r squared. And here r is positive, and theta lies between 0 and pi over 2. Okay, that is in polar coordinates. Now geometrically, what we have done is, in fact, we have taken a point in the xy coordinate. Remember, x, y are both positive, 0 to infinity. So a point on the xy coordinate system is then transformed through our transformation into a point that is represented in polar coordinates. And if you recall, the polar coordinates is just a half ray that emanates from the origin would be here. So all we have is just r, and every point is represented by means of r and theta, where theta is the angle in standard position. Okay, there you go. So that's what theta is. And of course we have would be this hypothetical dotted line which represents theta equal pi over 2, which would be synonymous to the y-axis in the xy coordinate system. Okay, so this is what we have. Now of course r is positive and theta ranges from 0 to pi over 2, so there you go, that's the range of theta. So we have this region. Okay, so that is our transformation. It is a one-to-one transformation, so therefore it makes it valid. Now, next we need to rewrite the double integral in xy as a joint function of xy, dy dx, using the polar coordinates that transforms into a region in r theta as a function, joint function of r theta, and of course we have times the absolute value of the Jacobian of the transformation, the r d theta. And the Jacobian of the transformation is going to be the partial of xy, dxy, over partial of, with respect to partial of r theta. Okay, so remember this is the d notation. Okay, and we use that quite often for the differential notation for functions of several variables. Okay, so what is dxy over dr theta? It's going to be, this is the determinant notation. Okay, so the notation for determinant is looks like absolute value. So it's going to be dx dr, and then we're going to have dx d theta. And then the second line is dy dr and dy d theta. Again, that's going to be the determinant notation. It is not absolute value. Now, the partial derivative of x, remember x is r cosine theta. So partial, when you take the partial derivative, let me write that here for reference again, and y was r sine theta. So when we take the partial of x with respect to r, we simply have cosine theta. We take the partial of x with respect to theta, then r acts as a constant, so it's going to be negative r sine theta. Okay, negative r sine theta, because derivative of cosine is negative sine. In the second line, the partial of y with respect to r is just going to be sine theta, and partial of y with respect to theta, r acts as a constant, derivative of sine is cosine, so we get r cos theta. Next, using the formula for the determinant of a 2 by 2, remember you multiply product minus product of the off diagonal. So multiplying the diagonal elements, we get r cosine squared theta minus product of off diagonal is going to be negative r sine theta times another sine theta in the lower left. Okay, and that's going to make it r, we're going to factor r indeed, that makes it cosine squared theta plus sine squared theta. And that's just r, which is positive, but in our formula for transformation, it does require absolute value of that, which is going to remain the same. Okay, so we are good to go now to our double integral with this new transformation. Therefore, gamma of alpha, gamma of beta is going to be 2 times 2 is 4. The double integral from 0 to pi over 2, those are the limits on theta, and these are the limits on r. So clearly I'm thinking the outside is d theta, the inside would be dr once I write the integral. Okay, then the expression was x squared, right? X2, not squared, but it was x to 2 alpha minus 1. X is r cosine theta to 2 alpha minus 1, and then y was r sine theta to 2 beta minus 1, and then it was e to negative parentheses x plus y. Well, let me go back here and show you. It's much easier right in here. So instead of x squared y squared, we're going to replace it by r squared. So it's going to be e to negative r squared. Okay. Negative r squared, and of course absolute value of the Jacobian, and then dr d theta. Okay, and then this is going to become for the integral from 0 to pi over 2, 0 to infinity of, okay, here we can combine the r's. We get r to 2 alpha plus 2 beta. I'm combining these r's, and remember there's an r here. So the exponent is going to be 2 alpha minus 1 plus 2 beta minus 1 plus 1. So that's just going to make it, let's see, 2 alpha. There we go, minus 1. I went ahead and multiplied this r also by the other two factors of r. Okay, now on the cosine, we have cosine theta 2 alpha minus 1, and we have sine theta 2 the power of 2 beta minus 1 e to negative r squared, and then dr d theta. Okay, now in the next step, we're going to actually break this up into two integrals. One's going to be from 0 to pi over 2, and then the 4, I'm going to write it as 2 times. Let's have the trig functions cosine theta to 2 alpha minus 1 times sine theta to 2 beta minus 1. Okay, and then d theta. So I got all my trig functions, say together, times integral from 0 to infinity of 2 times r to the power of 2 alpha plus 2 beta minus 1 e to negative r squared, and then dr. Okay, now clearly what's in here, the first integrand, we recognize this as the trig form of the beta function. Therefore, gamma alpha, gamma beta is going to equal to, that's more specifically beta function of beta alpha. This part is the beta, this part is the alpha. Okay. And of course, because beta function is symmetric, we are okay to write this as beta alpha comma beta times, I'm going to call this integral the ladder integral. This one, let's call this time that integral I. Okay, now, because we need to evaluate this integral now. Okay, once we do, and then we can bring it back here and finish this. So the integral now, I'm just going to write it as 0 to infinity r to the power of 2 alpha plus 2 beta minus 1 times e to negative r squared times 2 dr. Now what I did, I moved the 2 in front of dr in just a moment. I'll explain why I did that. Okay, and the reason for that, of course, let me show you, is because I'm gonna let m be r squared, so that r is equal to square root of m, and because r is positive, square root of m has to be positive. Okay. Now in m equal r squared, if you take the derivative, then dm is going to be 2r dr, and of course 2 dr is going to be dm divided by r. Right, so I can say that 2 dr is therefore dm divided by r, which is the square root of m. Okay, we're going to need that over here in just a moment. All right, so let's see. And of course, the limits of integrations are not changed, because when r is 0, when r is 0, m is 0. When r approach infinity, so does r squared. Therefore, m approaches infinity as well. Okay, now let's actually work this integral. So this is going to equal to the integral from 0 to infinity. Remember, r is the square root of m, so it's m to a half to the power of 2 alpha plus 2 beta times m to a half. Remember, that's r. This is r to -1. I'm writing r as a square root of n to -1, right? Because we're changing it from r to m, times, now 2dr, remember 2dr is dm over square root of m. Well, division by square root of m is like m to a half to -1 power, right? And of course I have e to negative r squared, which is m, and then here I have dm. Okay, so everything is now rewritten in terms of the new variable m. So this is going to equal to the integral from 0 to infinity. Now we can combine all the m's here, right? M to a half to 2 beta, oh sorry, it's 2 alpha plus 2 beta. I rewrote it twice, 2 alpha plus beta. That's going to be simply m to alpha plus beta. Okay, these two, m to negative a half times m to negative a half, well, that makes it m to -1, right? And then e to negative m dm. Good. And we'll be done in just one more step. In our next step, we're going to combine the two factors now. So that's going to make it m to the power of alpha plus beta minus 1, e to negative m dm. Okay, and of course this is gamma of alpha plus beta. Remember what I had earlier, 0 to infinity of, what was it, u to alpha minus 1 times e to negative u du. This was gamma of alpha. Remember we had that earlier? So this would be gamma of alpha plus beta. In other words, this alpha plus beta acts as the alpha here. Okay. Perfect. So we are done. Indeed, we're going to substitute now, remember, in I, which is up here. Substitute in here, and we almost have that desired relationship. So that gamma of alpha, gamma of beta is going to equal to, I'm going to swap out the alpha and beta in my beta function, times gamma of alpha plus beta that we showed, and from this beta of alpha, beta is going to be divide both sides by gamma alpha plus beta. We get gamma alpha, gamma beta times gamma of the sum. And that's what we wanted to show. Okay. Again, I have several videos where I used different methods of showing this, different ways. And there you have it. We did what we wanted to. Thanks for watching, everyone.